for the first inaccessible, and we got it for the first malus. So this is a joint work with Jordi and Stevo. And before going to what a consecutively large family is, I will give some motivation for the problem. So, and the motivation is in Banach spaces. If you have a sequence in a Banach space, you say it is subsymmetric if there is this constant C. And you have, let me see here. So you have that for any finite combination with the same scalars, the norm of these guys are similar to the norm of those. And notice that I need increasing sequences. So as far as I have increasing indices on X, on the sequence, and the same scalars, the norm of the combination looks like the same in these two sets. So this is a subsymmetric sequence. And so the most simple examples are the unit bases of C0 and LPs. It is easy to compute and prove it is subsymmetric. Then you have the unit basis of the Schreier space, which has no subsymmetric sequence. So this is the easiest example of a sequence with no subsymmetric subsequences. And the most famous space which has no subsymmetric sequences is the Siroson space, which is a separable Banach space, which is reflexive and has no subsymmetric sequences. It was actually constructed in order to get an example of a Banach space with no copies of LPs. But the important, in order to get rid of the LPs, actually you get rid of the subsymmetric sequences. So, and Ramsey principles imply in general that large uncountable structures have no have indiscernible sequences. So you can see this notion of a subsymmetric sequence as something like indiscernible in model theory. And so it should be the case that for large Banach spaces, you always can find subsymmetric sequences. And it is the case. So we are interested in understanding what is the minimal cardinal such that any Banach space of that density has a subsymmetric sequence. Okay, so there are two questions. We are mainly interested in the reflexive case, okay, which is more difficult actually. So the first result shows exactly that this large, if you have a Banach space which is very large, then it does not have, it always has subsymmetric sequences. So, and the cardinal is the omega Erdős cardinal. So we have an upper bound for that cardinal we defined here. So the minimal cardinal. We have this upper bound, and we would like to know what is this cardinal. So Argyros and Motakis got last year an example of the Siroson space gives that this cardinal is at least uncountable, right? Because we already have a separable Banach space with no subsymmetric sequences. So then Argyros and Motakis got an example of a reflexive Banach space of density continuum with no subsymmetric sequences. And my purpose here is to present the result we got that for kappa smaller than the first malo cardinal, there is always a reflexive Banach space of density kappa with no subsymmetric sequences. I will present it in the way we got, so first going to the inaccessible and then turning to the malo, so to show what's the job we have to do. So far what we know is that this cardinal is between the first malo and the omega Erdős, right? This is what we get from this list of results. Okay, so let me try to explain what kind of combinatorics is involved in proving that a Banach space has no subsymmetric sequences. So if you have an index set, we have a family of finite subsets. containing singletons. And then we have these three notions. So hereditariness, meaning it is closed under subsets. Compact, meaning it is compact as a subspace of 2 to the index set. And it is large if for every infinite set of the index set, you have elements in the family. So you have elements in the family as large as you wish, right? And then we have the Schreier family, which is compact, large, and hereditary on omega. And so, and given a compact hereditary family on an index set, we can define a norm on the C00 of I, which is the finitely supported vectors on I. We can define this norm depending on the family. So we take the maximum, okay, there is this condition with the sup norm with the maximum norm just to guarantee this will be a norm. And then you have this supremum of all possible combinations of the, so you take the L1 sum of the coordinates of your vector, but only for sets in your family, right? Instead of taking the sum of all of the xn's, for example, which would give you the L1 norm, you take only for the indexes in an element of the family. So this is a norm in this space, and then we can consider the completion of it, and we get a Banach space. So that is this. So why is it difficult to get? Well, let me maybe first say what the results say. So Jordi and Stevo proved that if kappa is not omega r-, then there is a non-trivial weakly null sequence with no subsymmetric basic subsequence, and that it is equivalent to be to have a large compact hereditary family on kappa. So building these large families, being able to build a large family on a cardinal kappa means that you have some sequence with no subsymmetric sequences, okay? But it is only about one fixed sequence. You have nothing about the whole Banach space, right? You are just looking at subsequences of that sequence. So, so let me now go into how. So this first part about the large families, this is about just one family, right? There is no consecutively large, which I will still say what it is, and gives you only about one sequence. So we will exactly go to more families in order to get the property for any sequence in the Banach space. So I will try first to go, okay, this is actually not correct, right? It should be 2000 because it was inaccessible, so anyway. So let us go to this problem about any sequence in the Banach space. What are
over here? What is the length of this? When you say no subsymmetric sequences, so the length over there is of
sequences meaning countable sequences.
Omega.
Yeah, omega sequences. It's not, yeah. So this is the problem, right? You have a large space, so you have many of those, and you have to control all of them.
And always finite for every n. You can find any finite.
I guess he was asking for sequences longer than.
Yeah. Yeah, longer sequences, which would be easier. Yeah. So what are the main ingredients in the proof? So first of all is this interpolation method and the Sirius-on space, which I will give a rough idea of what it is, which links the problem, as before, links the problem of finding sequences, these consecutively large sequences, and having a space with no subsymmetric subsequence. Okay, this is where the link is between the two things. Then there are the CL sequences which on chains, which I will explain what it is. Then we have the key result, which is about CL sequences on trees. So before these CL sequences on chains will be just CL sequences on on some partial order, and then I will go into trees.
What are CL sequences?
Consecutively large. I
Oh.
will define later, but it's the consecutively large. Yes, sorry. And then there are these walks on ordinals in order to reach the malo to reach every cardinal below the first malo. Okay, so these are the 4 ingredients we have. Let us go to the interpolation method, which gives the link and motivates why we define these CL sequences. Okay, so we have again the vector space of finitely supported functions. And then I have this canonical element which has only one coordinate 1. And then I have a norm on C00 of omega, so on the countable setting, and where you have these ENs being one unconditional basic sequence, and I have the completion, so I have a Banach space, and I have a family of sequence of norms on the C00 kappa, okay? And where this sequence is always a C unconditional basic sequence, and again, I take the completion of it, I get another Banach space. So I have all these xn's, which are Banach spaces of density kappa, right? And I have this x, which is a separable Banach space. And then I combine all these norms by doing the following. So I take sums of the norm of an element in C00 kappa. I compute the nth norm, and I take this sum, and then I compute the norm in the Banach space I had in the countable level. Okay?
What is C unconditional?
C unconditional is that the norm does not depend on the signs you have on each coordinate, so you can change the sign 1 or -1, and the norm will be the same. Up to C, yes. Up to C. So, and then I can take the completion also of this space. Okay, so we use hereditariness and compactness to prove that these are all norms and so on. Okay, you have to do some computations, and that also E alpha will still be a C unconditional basis on this space with this norm, with this interpolated norm. And now in our context, we will use for x, so in the countable setting, we will use the Tseruson space, which has no subsymmetric sequences. And we will define these norms using the CL sequences. So I will have a sequence of norms on a cardinal kappa, a sequence of families on a cardinal kappa. And using each of these families, I define a norm. And then I interpolate as before. And I prove that the obtained space, the interpolated space, contains no copies of C0 and L1. And then I conclude this is a reflexive space. And then this is very rough idea, okay? If I have a subsymmetric sequence in this interpolated space, I can show that either it has a relevant part, which I put here, in one of the xn's, or it has a relevant part in the countable one, which you used to interpolate all of them, right? And so the Tseruson space has no subsymmetric sequences, so this second alternative cannot hold. So I know that one of the xn's has a subsymmetric sequence. It's not really that it has a subsymmetric sequence, but it has some relevant information of it. And then I work with this subsymmetric sequence in xn. So I get finitely supported vectors by approximating, and then I refine it using, make some difference to get weakly null convergence and so on. So finally, what I get from the original subsymmetric sequence, I get a sequence, say, with disjoint supports. And remember that this finite and disjoint supports. And remember that this the norm in this space is computed by using exactly elements of the family. So I get these elements of the family where the relevant part of the norm of the of the, maybe let me write some. I have a sequence, finally, and when I try to compute, let me put K, when I try to compute the nth norm here, I get some set, say, Sk, right? Because this norm depends on elements of the family. And then, then I get a sequence in my family Fn. So I get a sequence in my family Fn, and this consecutively large will say that whenever you have a sequence in the family Fn, you can pass to a subsequence such that you have arbitrarily large unions of these elements in the next one. So I know that some Sk1, Skl, say, will be in Fn plus 1, okay? For L arbitrarily large, I can get such an element. And then this will give me the contradiction, because then I will have in the Xn plus 1 space something like L1 or something, which I know that I don't have. So this is roughly the idea, and this is the motivation for defining this consecutively large. Whenever I have a sequence here, I can pass to a subsequence when I get unions of it in the next family, okay? So this is, yes, this is the idea of the proof, which links existence of these families with existence of a Banach space of density. So the density will be the cardinality of the index set, right? With no subsymmetric sequences. So let us go to what these CL sequences are. So I have a partially ordered set, and I have two families which are formed only by chains on this partial order. And I say that F is G large on chains. If something similar as here happens, but I restrict myself to sequences whose union is a chain in the order, okay? So whenever I have a sequence in G, such that the union is a chain in P, there is a subsequence such that I have these arbitrarily large unions of elements of the subsequence in F.
Subsequence of what?
Subsequence of Sk, sorry. Okay. So I have this condition here, saying that it's a little bit weaker than that, right? Than what I stated before. Well, not a little bit; it's a lot weaker, actually.
Calling the index T is somewhat unfortunate in the last line.
Yeah, because TT, right? But you won't reach it, so it's okay. Yes. And notice that if P is totally ordered, then everything is a chain, so then you don't have this restriction. And this is what I was talking about here. So we will actually want to find CL sequences on ordinals, so it will be of this kind. But in order to do so, we will pass first through families on trees. Maybe I will write this definition here in order to keep, for you not to get completely lost. So, or maybe I will write directly the next one, which is more. So now I have a sequence of families, and I say it is consecutively large on chains of the partially ordered set P. If the first family is just all the singletons, and then each family is compact and hereditary, because I want to define norms using this family, so I have to keep that. They are increasing, the sequence is increasing, and one is always large respective to the previous one. So I will put here F0, the singletons, F1, compact hereditary Fn contain, and this is which means that for every sequence here I can pass so there are, let me put like this, pk1, pkl, such that the union yes, let me restrict to the chain, yes. Here, right? I have the, so yeah, this is everything on a partially ordered set. So now our purpose is to construct these families. So construct these sequences of families in all ordinals below the first mallow. So let us start by, sorry, yes.
So the fact that this is an infinite sequence doesn't seem to
Sorry?
So you have this infinite sequence, that's
Yes.
A, and you can extract a subsequence such that there are arbitrary finite.
If you like, this subsequence is
also
relevant.
Yeah, that's, I mean, if a
For
subsequence.
every-
Yeah,
every
in
subsequence,
this,
because of Ramsey, but doesn't matter how you write it, it's the same. Means that there are arbitrary everywhere.
yeah.
This is the thing. Unions everywhere.
Okay. So let us start with omega. So if when our index set is omega. So in this case, we take just F0, we have no options, we take the singletons, and then we make this operation, which takes, so Fn plus 1 is unions, so finite unions of elements of Fn. Okay, this is what this operation is saying. Which are ordered, so the maximum of one is smaller, so they are in block position. And moreover, the family, the set of the minimums of all of them belongs to this family. And actually, and this is the Schreier family, these are the singletons, and here I am taking, so I am adding to each element of the Schreier family 1 point. And the thing here is when I take a sequence in Fn, I can pass to a delta system, and then I have, so the root will be in Fn cross, well, it is not cross, it's, yeah, it is cross. So it will be in the root, because the Fn is hereditary, so the root is a subset of all of them. In particular, it is in Fn. And then all the other parts, they are in Fn. And with them, I can wait until the minimum of them get large enough in order to get this in the Schreier family. Because the root would pose me a problem in order to get this set if I have the minimum of the root too small, it wouldn't be in the Schreier family. So one has to check, but this is, I didn't write it down. So, but this is a CL sequence on omega. So whenever you take, well, one has to check hereditariness is easy, compactness, and then this largeness. This property here, which is the point. So, and now we want to go further, right? So we start with omega, and we want to go up to the first mallow. So first, maybe first up to the first inaccessible. So let us see some easy facts first. So if you have a cardinal which supports a CL sequence and you have a tree of height kappa, then T supports a CL sequence on chains. The point is that you have your tree here, and then you can take the height of each element of each node of the tree, right? So I have here kappa, and this is the tree. And now I know that here I have a consecutively large family, and I can take the family, say, of all chains, so finite chains of T, such that the image is in the family here, right? So I pull this back from kappa to the tree, only on chains, and then I get the CL sequence on chain here. So, so I can pass from a cardinal to any tree of the same height. And again, I want to emphasize this, that the fact that when I am working with a totally ordered set makes that the fact that this is a chain is not a problem. But whenever you have a tree, for example, from getting a sequence which has this property on a tree to pass to a sequence which has this property without the restriction on chains on the tree, this is actually the most difficult part of it, we will see. So this restriction is very strong somehow. And here I am passing exactly to a CL sequence on kappa, to a CL sequence on chain. So meaning that I have unions, I have arbitrarily large unions as far as I keep on chains. So then if I have kappa supporting a CL sequence and T less than kappa branching tree, then the set of immediate successors of every node supports a CL sequence. This is trivial. Again, I am thinking of the immediate successors with no order. So here is also, there is, well, maybe here it's a little bit confusing because you could think that there are only the only chains are the points, right? But actually what I mean here is that I have arbitrarily large unions and I have no restriction on that. Because immediate successors, there are no chains, right? So it it is not about CL sequence on chains that I am speaking here. So you just put a CL sequence on the, you just copy a CL sequence from kappa to the immediate successors. So this is the, and now the key point, as I was saying before, is to pass from a CL sequence on chains of 3, which, for example, when I have one on the height of the tree, I know I have it, and from a family of from CL sequences on the immediate successors of each node of the tree. So to pass from these CL sequences to a CL sequence on T, but meaning that now I am not restricting myself only to chains, right? When I say here T supports a CL sequence, it should be that the cardinality of T supports a CL sequence, right? This is the, because I don't want the restriction on chains anymore. And this is the main result in order to step up, because now if I have, for example, less than kappa branching tree of height kappa, right, then I know I can get this CL sequence because of this easy fact. I know I can get these CL sequences because of that. And then I can pass to the whole tree. So I increase the cardinality. So let me think. Maybe let me, before, no, let me say first some of what is involved here, because then I think I will go, yes, not on chains. And yes, this is what I just said. Okay, so I have some details here, yes. So let me say what is the idea of the proof of this theorem. So let us fix first of all, let us fix a family on chains of the tree, and for each node, a family on the immediate successors of T on the tree. And then I have this functor, which associates to these two families, well, to the family C and the family of the families ATs, the following family. So all subsets of T, where every chain of the subset, well, not only of the subset, but of the generated subtree belongs to C. I will say a little bit more about that. And for every node, the set of immediate.
Generated subtree?
Sorry?
Oh, generated by what?
Generated by S. So yes, I will have to go a little bit into that. Actually, I want to go a little bit into that. Whenever I have a subset, it's a finite subset, right? We are always talking about families of finite set. So whenever I have some, so let me go like this. Here, this. So I suppose I have, or this, suppose I have this set on a tree. So the generated subtree, which I will consider here, yes, is, I will take, so the minimal tree which contains all these points, so I will have to take all these mids here, but also I will add not only the mids, but I will add also the immediate successors of mids, which are below one element of S, right? So I should have put it in different colors, right? Because now we don't know what is the tree and what is the, for example, if this was the set S, then the generated subtree, I add these 3 points, but I also add, for example, suppose this is already the immediate successor of this, but I add the immediate successor to this point because there are those above, and I add here one and here one, and this is it, right? And the tree may have other, but since I don't have S in the other branches, this is, so this is the generated subtree, the tree generated by S. And this is the subtree I am considering. So again, I have a family on chains of T, and I have families on the immediate successors of each node. Then I take sets of the tree, and I look to the generated subtree. And if every chain of it belongs to the family of chains, and every set of immediate successors of T belongs with respect to S, so the subset of S belongs to the corresponding family in the immediate successors, then I add it to the family F. So
this is finitely branching then.
What is finitely branching?
We are talking about finite set. The set of immediate successors of T has to be finite.
No, the set of immediate successors of T here has not to be finite. And I look to all of them.
Immediate successors of elements in S. So you have the T, and only for elements in S, which are, of course, on top of this T, and you see which is immediate successor, and you collect all of them.
So for example, this set here, right? I have my S here, and I look to this, and this has to be yes, in the subtree. Yes. In the
So
subtree.
with respect to S means in the generated subtree.
Yeah. Yes. This is it. Yes. Okay. So, and this functor, whenever I have compact and hereditary families, it is not difficult to prove. That the corresponding F is compact and hereditary because, well, the chains are, well, just because the corresponding properties of those families. There is not much to do. And then the tricky point is to prove that whenever I have a CL sequence on chains of T, and I have a CL sequences on sets of immediate successors of each node of the tree, then I can find a CL sequence which is on T, meaning that it is on the cardinality of T, right? On the set of the nodes when I see this totally ordered. So it is not exactly, I have to increase these original sequences here by making finite unions of them and the same kind of operations as I did for the example on omega, for example. And then take the corresponding F families and prove that it is CL, so consecutively large. Just to say a few words about this argument, which is the hard part of the problem. Suppose you have, so now we can think that all these families are formed by subtrees, right? By trees generated by finite sets in this sense. So whenever I take a family of subtrees, a sequence of subtrees of T, I want to refine it in order to get arbitrarily large unions of them in the next one, right? This is what I want to do. So what I do is, first I use, so I pass, for example, to a delta system, and then I start analyzing some of the points. For example, some important points of the root of this delta system. I have a delta system of subtrees, and I analyze, for example, maximal elements of the root are important for us. And then I make, using many times Ramsey theorem, I get some kind of, I pass to a subsequence which has some, how to say this, where I can control some things. So for example, consider a sequence of subtrees, and now look at the tree generated by the union of them, right? So you have, we started with finite trees, and then I look to the tree generated by the union of them. This is already an infinite tree, and I have added new points because, for example, if I had this, broke the thing. I guess it's like that. So they will be angry with me, right? If I if I just let me try once more, and then if not, yeah, seems like. So, for example, if I have two, let's put two S1 and S2, two trees here, two sets here, but let's think that they are already trees, right? So I have already all these points in the green one, and now I have, for example, another one which is like this. I have to close it so it is something like that and like that, for example, right? And now still I have no new points here because I didn't mix them enough. So for example, here, where are they? Yes, so I have to find the new points. So for example, let's suppose here I have a green, yes. And then, for example, I have this new point, right? In the generated subtree, I am adding this point, right? When I take the union of these two sets and take the generated subtree. So I have all these new points which are either meets or of different trees, or they can be also immediate successors of parts of different trees. So I start an analysis of all these new points I am adding, and I have to somehow control them. And the key thing is to get a subsequence where whenever where I have finite sets. So let me try to draw a picture here. Let me maybe copy from the picture I had because it would be more safe. Yes. So I have two, I can refine the sequence of SNs so that I have two finite sets, such that whenever I have one point in this in this large generated subtree, I have two finite sets F and A, and I know that there is one element, for example, of F, so this is in F, such that this part is only in one tree, okay? And the chain below this guy, for example, is already controlled. It is already in the, it's too complicated to explain, now I know this. So, okay, let me just say that we can control these new points I am adding. They are not finitely many, but I can somehow canonize them and control them by finitely many of them. This is what I can say. Both the mids and the immediate successors, we do different things for each case, and we control all of them. And then we, using this canonization, we can get that some arbitrarily large unions of this subsequence will be in the next one, because then I have finite things to control, and I use Ramsey theory to do this, okay? So I think this is what I will say about this theorem. This is the hard part, as I said. And yeah, okay, so here I stated the theorem again. So now I can pass from families on chains on a tree, which can easily be constructed by CL sequences on the height of them, and families on immediate successors, to CL sequences on the whole tree. So, and this is how we get the CL sequences below the first inaccessible. Now we have this corollary. If kappa supports a CL sequence, then 2 to the kappa supports a CL sequence, because exactly I have a tree, right? So if kappa supports, the height supports, I pass 2 CL sequence on chains of 2 to the kappa, and each node branches only into 2. So, and for finite this is trivial. I have CL sequences on immediate successors, and then I get CL sequence on the whole tree. And
how do you get through the singular strong limits?
To the?
Well, there is another tree. You use a singularity, and then you will step up. It is a similar result than that.
All right.
You're going to simplify it over a really simple-minded tree.
Yes. A very, very small one, yes.
Just branch at the root and don't do anything.
Yes.
Okay, so this is the result for first inaccessible. And now let me say a few words how we get the result below the first mallow. So suppose we have a small C sequence on a cardinal kappa, meaning a family of C alphas, such that each C alpha is a club in alpha with the order type equals to the cofinality of alpha. So this is the C sequence part. And then there is this smallness part, which says that I have a function f from kappa into kappa, which controls, I know that the order type of each C alpha is smaller than f of the minimum of C alpha. So I know the order types of C alphas are controlled by this function, okay? And so then, yes. So then the theorem says that given a small C sequence, if I consider rho 0 this function, so from pairs on kappa into finite sequences of subsets of kappa, which just takes I walk from beta to alpha using the C sequence, and I take the initial parts of them, the parts of them which are below alpha. And then the tree, which I get from taking the restriction of rho 0 beta restricted to alpha, so for alpha less than beta, ordered by end extension as functions. So this is a function, and I say one is below the other if it extends, so the other way around, one is above the other if it extends. And so this is a tree with cardinality kappa and which supports a CL sequence. This is how I get, so let me go further. Yeah, maybe there is the corollary, but it does not say that any, but I guess, yes, so here is the lemma. If I have a strong limit cardinal below the first mallow, then it supports a small c sequence. So it has a sequence like that. And therefore, this tree supports a CL sequence. And if C alpha is a small C sequence, and every cardinal less than kappa supports a CL sequence, then this tree supports a CL sequence on chains. So this is, again, here I want a CL sequence, right? Not only on chains, but I do the same thing. I first go to CL sequence on chains, and then CL sequence on immediate successors, and then using our main theorem, we get the CL sequence on the whole tree. And here, just to give a vague idea of what's going on, so let me see. So suppose I have two partially ordered sets, and this lambda is chain preserving, so a chain here goes into a chain in Q and is one-to-one on chains, so it is injective when I restrict it to chains. Then if I have a CL sequence on chains of each pre-image of an element of Q, and I have a CL sequence on Q, CL sequence on chains of Q, then I get this CL sequence on chains of P. This is say a result which generalizes the argument when you pass from a kappa to a tree of height kappa. This is something. So I didn't say, I won't say what these families are, but this is just a generalization of the argument of passing from a CL sequence on kappa to a tree of height kappa. So let me just mention here. So in order to conclude the proof of this, so now if I take kappa below the first mallow, either it is a strong limit and then it supports a small sequence, and if it supports a small sequence, and then I get a CL sequence on chains of the tree, and then using our main result, I get a CL sequence on the whole tree. Okay, so I reach kappa finally. And if it is not strong limit, then I do something similar as I've done before, right? I suppose everything below is, and then I can pass to the cardinal. So this is the argument for all cardinals below the first mallow. And just to conclude, so remember this was the cardinal we were interested, which is the smallest cardinal, such that every Banach space of that density has to have a subsymmetric sequence. And we know so far that it is between the first mallow and the omega Erdős because the old result of Newtonian. And the question is if we can go further with this construction. Okay, I think this is all I have to say. Thank you for your attention. Question, yes?
So, way back at the beginning, the definition of subsymmetric sequence, there was this constraint that you could only at similarly ordered tuples. The k's should be increasing and whatever the other one
Let us go back.
should be increasing. So this is somehow analogous to order indiscernibles in model theory. But in the examples like C0 and LP, it looks like the order doesn't matter. You can take them in shuffle around as well. So it's like you have a stable theory.
That's exactly why there is a word sum in front of it.
Yeah. So the question is, could one do a rerun of this whole talk with symmetric rather than subsymmetric sequences? What can one say about the corresponding cardinalities with
Wouldn't that be
symmetric
easy?
cases?
Then you can build
Wouldn't
any
that be
space.
easier?
I guess.
Yeah, it might be
Any
easier, but the cardinal might
density,
actually.
any
you
Any
might-
density
you can
has
reach
a-
it without.
Yeah.
You can reach, because there is this called Slumberg space, whatever it is, which do not have, and the construction can be,
Can be
this
drawn.
is in omega, but you can do it in any other
Ah,
cardinal.
okay.
So it's way easier. Yes.
More questions?
Well, there was a question of Tanmay which makes it easier, but then gives you different cardinal, which is to look at sequences of different lengths.
Yeah. But I guess this is easier, right? But yeah, but we at least to know what are the cardinal.
Yes, because
Oh,
it might actually,
yeah.
you might be able to show that this end reflect is one of those bounds.
Yeah. Mhm.
Well, I mean, it's not going to be a difference for omega L, because omega L is characterized by the Ramsey property.
Yes, you
You
cannot
can't
go
do more
above.
than that,
You
yeah,
cannot
because
go above.
you can code this as a monotheoretic statement. Even for us, this statement can be coded as a monotheoretic in the language control size continuum. So omega L is characterized by the instability that. So we can't go further, but of course you can go to a Ramsey kernel, maybe questions for the Ramsey kernel.
So you're saying alpha Erdős would give you sequences.
Yeah, means what I'm saying, if you want to do with alpha, with below omega Erdős, then there's no point going to a longer sequence. But if you want to get a longer sequence, then maybe you have to go to Ramsey
But-
or something.
Yeah, but maybe you could characterize by this longer sequence.
Well, that's probably correct. Easier because all these delta systems are much easier if you take omega on
Yeah,
sequence.
yeah, sure.
Yes, exactly.
Yeah.
So if you assume B equals L, can you go higher than Paulo?
I can tell you lots of things which I believe. These other two
So
characters
you may
are
use
always.
global square there.
I think that one can go. I think one can go at least about omega now,
Or even strongly now.
even more. But I think that's.
There is this whole question about half-dense families, which is actually also connected with the Schreier family. Seems to be very close to this, but so there is there also a large cardinal involved.
This is about finite. This is way more complicated, right? Every finite set must have a half or epsilon
That's right.
portion.
Yes.
Exactly.
This
This
finite
is
set,
tricky, yeah.
this is much more tricky than that. This is about any infinite sequence has
There is a
L
finite.
unions on the next. But I need to start with infinite.
Uh-huh.
You see, this is way more tricky.
This
This
is why
needs
you
a very
cannot go
much
this type, huh?
more detailed analysis of what you are doing. I don't think this will do anything.
Nice, yes.
Unfortunately.
And in fact, it was helpful to you to be this reflexive case.
Hmm?
It's sort of strange because your examples are reflexive and you would think it's harder, but it was helpful to you to know that you are reflexive so you can rule out.
But
those
actually-
values,
Because
not
if it's not reflexive, then you can argue with dichotomies, and then this cannot be. This is, I mean, she didn't explain something. On
Yes.
that, but it is because this is the example. If you have an example, it has to be like that. See, because of something else. Rosenthal one dichotomy and things like that. You argue like that, and you will find that it must be reflexive. The counterexample must be reflexive.
Reflex.
Even if you don't want.
Okay. There are no more questions, then thanks again. So next week, we all move to Norway.